And welcome back. As we go ahead and continue our cosmic journey, previously we had looked at visible light telescopes, but now let's go ahead and segue to looking at radio telescopes. So when we start talking about radio telescopes, we're of course not talking about the radio that's in your car, but instead radio radiation. In addition to visible and infrared radiation, radio waves from astronomical objects can also be detected from the surface of Earth. In fact, as early as the 1930s, Carl J. Jansky, an engineer at Bell Telephone Laboratories, was experimenting with antennas for long-range radio communication when he encountered some mysterious static, radio radiation that was coming from an unknown source. He actually discovered that this radiation came in strongest about 4 minutes earlier on each successive day, and he actually correctly concluded that radiation must be originating from some region fixed on the celestial sphere. Subsequent investigations showed that the source of this radiation was actually part of the Milky Way galaxy, and Jansky had actually discovered the first source of cosmic radio waves. So when we start talking about this detection of radio energy from space, it's important to understand that radio waves cannot be heard as they are not sound waves that you hear coming out of a speaker. Remember, it's not the same radio that we identify with of our stereo. Like light, radio waves are actually a form of electromagnetic radiation, but unlike traditional forms of light that we're familiar with, you cannot detect it with your senses. Instead, if we want to really find these radio waves, we have to rely on electronic equipment. In commercial radio broadcasting, this is typically done by encoding sound information into radio waves, which then must be decoded at the other end and then turned back into sound by either speakers or headphones. The radio waves we receive from space do not, of course, have things like music or other programming information in them. But if you were to take those cosmic radio sound signals and translate them over to sound, they would sound pretty much to you like static that you might hear if you were scanning between different radio stations. Now, there is information that is actually hidden in those radio waves, that not simply just static, but that static that might sound like that to us is actually going to have chemical and physical conditions of those sources of the waves. So let's talk about radio waves a little bit more. Just as vibrating charged particles can produce electromagnetic waves can make charged particles move back and forth. Radio waves can produce a current in conductors of electricity such as metals, and if an antenna intercepts radio waves, it can create a very feeble current in it. That current then can be amplified in a radio receiver, again not the kind that's in your car, until it is strong enough to measure or record. Now in astronomy, it's common to use sophisticated data processing techniques that allow thousands of separate frequency bands to be detected simultaneously. Now radio waves are reflected by conducting surfaces, just as light itself can be reflected from a shiny metallic surface, and according to the same laws of optics. Well, with that in mind, just think that a radio reflecting telescope has to have a lot of those same features then. We need to have a concave metal reflector, or a dish. The radio waves can then be collected by that dish to be reflected to a focus, where they can then be directed to a receiver and analyzed. This is not too dissimilar to how we operate with visible light. Now, because humans, though, are visual creatures, radio astronomers often construct a pictorial representation of the radio sources they receive. So let's look at an example of a visual interpretation. This image here shows us radio observations of a galaxy called Cygnus A. Colors have been added to this because, again, humans like pictures, to help our eyes kind of sort out the regions of different radio intensities. The red regions you see here, these kind of small blobular regions, are areas that are kind of the most intense, whereas the blue regions here are the least intense. Now, the visible galaxy, if we were to go peer up in the sky and look at that with our telescopes, is actually this small dot right here in the center. This is what we are looking at here. Now, the radio image, when we look at this tiny galaxy in comparison to the rest of the image, reveals jets of expelled material, more than 160,000 light years long, on either side of the galaxy. So we have, of course, tiny little galaxy and one big jet on this side, and another big jet being expelled over here on this side. And so that's going to get us into radio interferometry. A telescope's ability to show us fine detail depends upon its aperture and the wavelength of radiation that the telescope is gathering. The longer the waves, the harder it is to resolve fine detail in things like images or maps that we try to make. Because radio waves, by their nature, have such long wavelengths, they present tremendous challenges for astronomers who need good resolution. In fact, even the largest radio dishes on Earth, operating alone, cannot make out as much detail as the typical small visible light telescope that might be used in a college astronomy lab. So in order to overcome this difficulty, radio astronomers have learned how to sharpen the images by linking two or more radio telescopes together electronically, called an interferometer. So, what does it actually look like? Well, in order for these interferometers to be together, we have to actually use them as an array. So, interference is a technical term for the way that multiple waves interact with each other when they arrive in our instruments. Now, because this is not necessarily the definition of interference that we might normally think of, it's better to think of this as how the resolution of this interferometer depends upon the separation of the telescopes, not upon their individual apertures. So we have, let's say, two telescopes separated a kilometer wide. They would actually give us the same resolution as a single dish, that is 1 kilometer across. And if we want to get even better resolution, astronomers combine many radio dishes into a single array. In effect, such an array works like many two-dish interferometers, all observing the same part of the sky together. And then we can use computer processing of whatever data that we've collected to really reconstruct a high-resolution radio image. Now, the most extensive instrument in the U.S. is the National Radio Astronomy Observatory's Yankee Very Large Array near Soroka, New Mexico. It has 27 movable radio telescopes, all on railroad tracks, each having an aperture of about 25 meters, spread over a total span of 36 kilometers. So it's a pretty large array. Now, by electronically combining the signals from all the individual telescopes, this array permits the radio astronomer to make pictures of the sky at radio wavelengths comparable to those obtained with a visible light telescope. Now, what if we want to increase that resolution even further? Well, initially the size of the interferometer arrays was limited by the requirement that all the dishes had to be linked physically together. So the maximum dimensions of the array were, at most, tens of kilometers. However, larger interferometer separations can be achieved if we say, hey, these telescopes don't have to be physically wired to one another. Astronomers, with the use of current technology and computing power, have actually learned how to time the arrival of electromagnetic waves coming from space very precisely at each telescope and then combine the data back later. If the telescopes are as far apart as, let's say, California and Australia, the resulting resolution far surpasses that of visible light telescopes. And so that's going to lead us into this another technique that we can use known as radar astronomy. Radar is the technique of transmitting radio waves to an object in our solar system and detecting the radio radiation that the object reflects. The time required for the round trip can be measured electronically with great precision because, well, we know the speed at which radio waves travel. We can then determine the distance to the object or a particular feature on its surface. Radar observations have been used to determine the distances to planets and how fast things are moving in the solar system. In addition, radar observations have navigated spacecraft throughout the solar system, determined the rotation periods of Venus and Mercury, probed tiny Earth-approaching asteroids, and allowed us to investigate the mountains and valleys and surfaces of places such as Mercury, Venus, Mars, and even the large moons of Jupiter. So what do these large radio telescopes actually look like? Now, any radio dish can be used as a radio telescope if it is equipped with a power transmitter as well as a receiver. For many years, the most spectacular facility in the world for radio astronomy was the 3.5-meter telescope at Arecibo in Puerto Rico, as shown at right. Now, this telescope was too large to be pointed directly at the different parts of the sky. At 3.5 meters, this is pretty chunky. Instead, what they actually did was constructed in a natural bowl formed by the hills that were surrounding it, and was lined with reflecting metal panels. Now, a limited ability to track astronomical objects was achieved by simply moving the receiver system, which was suspended on cables 100 meters above the surface of the bowl. Unfortunately, this telescope was seriously damaged by powerful storms in 2020 and had to be decommissioned. Now, there is, of course, an even larger radar telescope. It's the 500-meter telescope in China that is called the 500-meter Aperture Spherical Telescope, or FAST, which is going to achieve similar things.